In the previous lecture, we have discussed Euler's angles in very detail. And you have seen, while discussing the three Euler's angles, we obtain actually three orthogonal transformation matrix. And the product of all those three transformation matrix gives the total transformation matrix or the complete transformation matrix, which is also an orthogonal matrix. Okay. Actually, utilizing these transformation matrix, we can see a very important concept, and this is actually the concept of finding components of angular velocity of a rigid body. Actually, in our forthcoming lecture, we will discuss Euler's equations of motion. And actually, I will discuss the Euler's equations of motion by two methods. First one is known as Newtonian method, that is, we will apply simply the Newtonian mechanics and derive the Euler's equation of motion for rigid bodies. And after that, we will see the Lagrange approach, or by the use of Lagrangian formulation of mechanics, we will also find out the Euler's equation of motion. When you will apply the Lagrange approach for dealing with the problem of Euler's equation of motion, then you will need the components of angular velocity of rigid body, particularly with respect to the body set of coordinate axes. Okay. And apart from this, when we will discuss a very important problem, the problem of motion of symmetric top, then again you will need to know the expressions for the components of angular velocity of a rigid body, particularly with respect to body set of axes. Okay. So it is necessary to know how we can find the components of angular velocity of a rigid body. Although in this lecture, we will discuss not only to find the components of angular velocity of a rigid body with respect to the body set of coordinate axes, but also with a space set of coordinate axes. But the first part of the lecture will be regarding the calculation of components of angular velocity of a rigid body with respect to the body set of coordinate axes, and that is more important. Okay. But when an independent question will be asked, it is possible to find the components of angular velocity of a rigid body with respect to the space coordinate axis. Okay. Or a space set of coordinate axis. Okay. You know that the angle of rotation is not a vector when it has finite value. It means when the angle of rotation is large, it does not follow the commutative law of addition, and so it does not behave like a vector. But when the angle of rotation is infinitesimally small, then it obeys commutative law of addition, or you can say the triangle law or parallelogram law of addition, and it behaves like a vector. So when we consider that in time t, a body gets rotated by an angle, let us say alpha, then d alpha by dt is defined as angular velocity. Okay. And as you know, in case of motion of rigid body, we consider three angle of rotations which are called Euler's angles. And you have learned about these Euler's angles in the previous lecture in very detail. You know, these Euler's angles are represented by the symbol phi, theta and psi. And what are these phi, theta and psi? You have already learned. You know that phi is the angle of rotation about the space z axis. Space z axis, it means the body is rotated by angle phi with respect to the z-axis of a space coordinate system, that is angle phi. And this angle of rotation theta is what? This is actually the angle of rotation about the line of nodes. When you say line of nodes, that means this is actually x1 equal to x2 after first rotation. When the second rotation is made about that new position of x-axis, that is called line of node. And about this line of node we make the second rotation, that is theta. And this psi is actually the angle of rotation about the body z axis, which is called z dashed axis or z prime axis. Okay, all these things you have already learned. Now, as all these three Euler angles are angles of rotations about the different lines or different axes, so their time derivative will give the angular velocity of the body about that line or that axis. So corresponding to the Euler's angle phi, we define the component of angular velocity denoted by the symbol omega phi, and this is defined as d phi by dt, or in dot symbol you can write this d phi by dt simply as phi dot. And what is this omega phi? As I have told you, this is just angular velocity about z-axis, space z-axis, because phi is the angle of rotation about the space z-axis, so its time derivative will give angular velocity of the body about the space z-axis. Okay. Similarly, you know, this theta is the angle of rotation of the body about the line of nodes. So its time derivative d theta by dt, which is denoted by theta dot, that will give omega theta, and this omega theta is called angular velocity about the nodal line. Okay, and the time derivative of the third Euler angle d psi by dt, which is denoted by psi dot, that is equal to omega psi, and this omega psi is angular velocity about the body z dashed axis. Okay, so you can see in case of rotation of a rigid body, we have three angular velocities: omega phi, omega theta, and omega psi. Actually, you may consider these omega phi, omega theta, and omega psi as the three components of the angular velocity omega of the rigid body. But whenever you talk about components of a vector, definitely in your mind there is actually three axes along which you define the components. But are these velocities omega phi, omega theta, and omega psi along the three axes of a space coordinate system? Answer is no. Are these three components of angular velocity along the three axes of body set of coordinate axes? Answer is no, because you can see the first component omega phi is about the z axis, space z axis. Second component omega theta is about nodal line, and the third component omega psi, this is about the body z axis. Okay, so actually these three components of omega are not all either along a space set of axes or the body set of axes. Okay, so it is not convenient to use these components to describe the motion of a rigid body. Okay, it will be not convenient to discuss the motion of the rigid body in terms of these three components. Okay, therefore you can say that the rigid body equation will be described. Actually, you will see later on, as I have told you earlier, that the rigid body equations will be described in terms of the body set of axes in general. Generally, whenever we will write the equation of motion of a rigid body, we prefer to write down the equations of motion in terms of body set of axes. Okay. Thus, we must calculate the angular velocity omega in the body coordinate system. And when you will try to find the angular velocity omega in body coordinate system, you will need the components of omega in body set of coordinates. Okay. Although I have told you in this lecture we will also see what will be the components of omega in a space set of coordinate system. Okay. But more important is to find the components of omega along the body set of axes. Okay. So you can see if omega is the angular velocity, then omega phi, omega theta and omega psi are actually the three components of omega. So the vector sum of omega phi, omega theta and omega psi will give the resultant angular velocity omega. Okay, in the body coordinate system. Okay? And actually we will find this omega. When you say we will find omega, it means we will actually find the x component of omega with respect to the body x-axis, which is denoted by omega x dashed. Okay, or you can also say that this omega is equal to omega x dashed I dashed plus omega y dashed j dashed and plus omega z dashed k dashed. Okay, so if your aim is to find omega, you have to find omega x dashed, omega y dashed and omega z dashed. These are the x, y and z components of omega along the body set of axes. Okay. Actually, for finding the value of omega x dashed, omega y dashed and omega z dashed, we will need the use of the four transformation matrices which you have learnt in your previous in my previous video on Euler's angle. So remember what I have taught you in my previous video. You must remember that. You have seen there was a orthogonal transformation matrix D which was defined like this. This is actually an orthogonal matrix and this is defined like this. I hope you can remember it. Okay. Now you know the inverse of an orthogonal matrix is simply equal to transpose of the matrix. If the matrix is orthogonal, then its inverse and its transpose are same. So since D is an orthogonal matrix, so D inverse is simply equal to dt, where dt is the transpose of matrix D. Okay. And how you find the transpose of a matrix? I hope you have definitely studied the matrix in your course in physics and mathematics both. So definitely you have an idea of finding the transpose of a matrix. Whenever you want to find the transpose of a matrix, we simply change the column to the to the row. So you can see the first column of matrix D is cos phi. The elements of first column of matrix D are cos phi minus sin phi and 0. So if you will find D inverse or dt, D inverse will be equal to dt. Why? Because D is an orthogonal matrix. So this will be just equal to transpose of D. So you can see this column has been made row. This is cos phi minus sin phi 0. You can see it here. And similarly, the second column is made the second row and the third column is made third row. In this way, you can find the transpose of this matrix or inverse of this matrix. Similarly, you have also seen the another orthogonal transformation matrix C, and that was defined like this. I hope you can remember it. Since C is also an orthogonal matrix, so C inverse will be equal to Ct and that will be equal to this much. Okay, and B, which is also an orthogonal matrix, transformation matrix, which was defined like this, so its inverse is equal to transpose of B and that is equal to this much. Actually, these expression for the transformation matrix will be used in finding the components of the angular velocity omega. Okay, and you have also learnt that actually the product of all these three matrices in reverse order, that is B times C times D, that gives the complete transformation matrix, and the complete transformation matrix is also an orthogonal matrix. Okay, so you can see the complete matrix transformation, which actually transforms the space coordinates x, y, z to the body set of coordinates x prime, y prime, z prime. It means when you want to find x prime, y prime, z prime, this column matrix can be obtained by applying the transformation matrix A on x, y, z. You have learned this thing in your previous lecture. Okay, and A, which is actually the complete transformation matrix, this is equal to the product of these three transformation matrices B, C and D in this particular order. And for finding this transformation matrix A, now let us substitute the values of these three orthogonal matrices B, C, D, and you can see it here. I have actually substituted the values. Okay. Now for finding A, you have to multiply all these three matrices. So first of all, multiply the second two matrices, this and this. And I hope you have definitely studied the multiplication of matrices, particularly square matrices. And after multiplication of the last two matrices, your result is like this. I am not giving the reading because I hope you have an idea of this. And now you will multiply this first matrix by this second. Okay, and after multiplication you get this. Okay, you can note down these things, and I hope you have a concrete knowledge of multiplication of matrix, which is very elementary, so you can do it. Okay, so in this way we obtain the complete transformation matrix A. Okay, and what are its elements, you can see it here. Now as I have told you that A is also an orthogonal matrix, mark this, and according to matrix theory, the inverse of an orthogonal matrix is simply equal to transpose of that matrix. Okay, so A inverse is also equal to 80. So if you want to find A inverse, what you will do? You will simply find the transpose of this matrix A, and for getting the transpose, what you do? You simply interchange the column and the rows. It means the column of the given matrix is made as row. First column will be first row, second column will be second row, and the third column will be the third row. So I have not written it here. You can obtain the value of 80, that is A inverse. Okay. All these things actually we will need for calculation, and you should remember this. For writing the answer in your examination, you must remember these things. Okay. Now let us see how we can find the components of the angular velocity omega of a rigid body with respect to the body set of coordinate axes. Now let us see. First of all, we are going to find the components of omega phi, and you have seen that omega phi is what? This is phi dot. This is phi dot, and phi is what? Phi is the angle of rotation of the body about the space z axis. Remember, in while studying the Euler's angle, you have seen the in first rotation the body is rotated about the space z axis. You can see, and by this angle phi, okay, about the space z axis. So since rotation phi is about the space z axis, so omega phi, which is phi dot or d phi by dt, that will be along the space z axis. Okay, so omega phi is lying along the space z axis. Okay, this is the direction of omega phi, and since it is along the space z axis, therefore its components along the body axis are found by applying the complete orthogonal transformation A equal to BCD. Because when you try to transform z axis to z dashed axis, y axis to y dashed axis, x axis to x dashed axis, you have to make the complete transformation, and for that you must use this A. So if omega phi x dashed, omega phi y dashed, and omega phi z dashed, these are the x, y, and z components of omega phi along the x, y, z components of body set of coordinate axes, then these can be found by operating the complete transformation matrix A on the component of omega phi along the x, y, z axis of the space coordinate system. Okay, as you have just seen, that if your aim is to find x prime, y prime, z prime, then you must operate A on x, y, z. Here at the place of x, y, z, we have omega phi x, omega phi y, and omega phi z. And at the place of x prime, y prime, z prime, you have this column matrix. Okay, and but you can see here that omega phi is completely along z direction, so its x and y components will be 0. If a vector is along z axis, then its x component, y component is 0, because this vector will make angle 90 degree to the x and y axis, and component of a vector in a direction which is perpendicular to it is 0. So omega phi x is 0, omega phi y is also 0, and omega phi z, this will be simply equal to phi dot, because omega phi is already in z direction. Okay. Now, for finding omega phi x prime, omega phi y prime, omega prime phi z prime, let us substitute the value of this complete transformation matrix A. You have just seen that this is your matrix A. So I have written it here. Okay. And this will be operated, or this will be multiplied with this column matrix 0, 0, phi dot. Okay. Now you can easily find the value of omega phi x dashed, omega phi y dashed, and omega phi z dashed. Let us see. When you will try to find omega phi x dashed, okay, how you will find it? We will take product of this with 0. See here, that will be 0, so I will not write. Then product of this second term will be with this 0, that will be also 0, so I will not write. And product of sine psi times sine theta will be with phi dot, so that will be simply phi dot times sine psi times sine theta. Is it okay? So omega phi x dash is equal to this much. You can see I have written it here that omega phi x dash is equal to this much. Okay. Similarly, when you find omega phi y dash, you will take product of this first element with 0, that will be 0. Then product of this second element with this 0, which will be also 0. And then product of this cos psi sin theta with phi dot. So this will be equal to phi dot times cos psi sin theta. You can see this is omega phi y dash. Okay. And now omega phi z dash. Again you will take product sin theta sin phi times 0, that will be 0, minus sin theta cos phi times 0, that will be 0, and cos theta times phi dot. So the z component will be phi dot cos theta. So you can see. So in this way we have obtained the components of phi dot, or you can say omega phi, along the x prime axis, y prime axis and z prime axis, that is x, y, z axis of the body coordinate system. In this way we have obtained. I think you have clearly understand this. Now if your aim is to find the omega phi vector, okay, which is actually the component of omega, okay, omega in body set of coordinate xa, yeah, with respect to the body set of coordinate xa, then we will simply add these three components multiplying by the respective unit vector. So this will be omega phi x dash I dash omega plus omega phi y dash j dash plus omega phi z dash k dash. And when you will substitute these values, you can see this phi dot will be a common factor, and the remaining terms will be this plus this plus this. Okay. So in this way we have obtained the x, y and z component of omega phi with in the direction of body x-axis, y-axis and z-axis. Okay. Now we will find all these three components of omega theta. Can you remember what is this theta? Theta is the second Euler angle, and this is actually the angle of rotation about the nodal lines or line of nodes. When you say line of nodes, that means x1 equal to x2 axis. Okay. Now if your aim is to rotate the x, y, z axis to the to x prime, y prime, z prime, okay, about this x1 equal to x2, then we perform orthogonal transformation B to come to the body axis after rotation theta. Okay, and hence the component of omega theta along x dash, y dash, z dash axis are obtained upon applying the final transformation B. So when you will operate the transformation matrix B on the components of this omega theta along the space x, y and z axis, then you will get the components of omega theta along the body x-axis, y-axis and z-axis. But you can see that this theta dot, which is omega theta, that is along the x1 barabar x2 axis. Okay, since it is along x-axis, so its y and z component will be 0. So you can see at the place of x component there is theta dot, but at the place of y component and z component you can see I have written 0. So when this B will be operated on this column matrix theta dot 0 0, you will get omega theta x dash omega theta y dashed and omega theta z dashed. Okay. Now you can see I have written the expression for this transformation matrix B. This is this much. You can see you have already learned this in the previous video. And this will be multiplied by this column matrix theta dot 0 0. So multiplication is very easy. Again you can see, if your aim is to find this omega theta x dashed, how you will find it? This will be cos psi times theta dot. So this is theta dot cos psi, okay, plus sin psi times 0, that will be 0, 0 times 0, that will be 0. So omega theta x dashed is simply equal to theta dot cos psi, okay. So you can see omega theta x dashed is this much. Similarly, you can find omega theta y prime, which will be this much, and omega theta z prime, which is 0. In this way you can find. So the omega theta vector will be simply the sum of these three vectors, and this will be theta dot times cos psi I dashed minus sin psi j dashed. So in this way you can see we have obtained the x, y and z component of omega theta along the body x-axis, y-axis and z-axis. Okay. Now finally we are going to find the components of omega psi along the body x-axis, y-axis and z-axis. But you know omega psi is obtained. Omega psi is equal to psi dot, and psi is the angle of rotation about the body z-axis, So omega psi is already along the body z-axis, that is along z dashed axis. Okay. So no transformation will be necessary in this case to obtain the component of omega psi along the body axis. Okay. So in this condition you can say that the column matrix omega psi x dashed, omega psi y dashed, omega psi z dashed, that will be equal to column matrix 0 0 psi dot, because this is along psi dot is along z dashed axis. So all its x and y components will be 0. So this is 0 and this is 0. Okay. And therefore here you can see that this omega psi x dashed is 0, omega psi y dashed is equal to 0, and omega psi z dashed is equal to psi dot. Okay. And in this case this omega psi is completely along k dashed vector, that is z dashed axis, and so this is psi dot k dashed. So in this way we have obtained the x, y and z component of omega phi, omega theta and omega psi. Okay. Actually what we have learned, now you can see I have written all those values here in a particular manner. You know, the x, y and z x component of omega phi, omega theta and omega psi. This omega phi x dash, this is the x dashed component of omega phi, which is equal to this much. We have already seen. You can, I am not turning the page, you can see. Okay. And omega theta x dashed is this much, omega psi x dashed is this much. Similarly, omega phi y dashed is this much, omega theta y dashed is this minus theta dot sin psi, and omega psi y dashed is equal to 0. And in this way you can also write the values of omega phi z dashed, omega theta z dashed and omega psi z dashed. Now when you will add all these x dashed component of omega phi, omega theta and omega psi, then you will get the x dashed component of vector omega, okay, of vector omega. So you can see the x dashed component of vector omega, if you write it omega x dashed, that will be equal to omega phi x dashed plus omega theta x dashed plus omega psi x dashed, okay. And you can substitute the values of omega phi x dashed, omega theta x dashed and omega psi x dashed. You can see in this equation 4 I have defined all those values. Since this omega psi x dashed is 0, so that will be simply the sum of first two components. And so this is equal to this much. Actually, I have derived this result, but I will suggest you must remember this, because when we will discuss the problem of motion of symmetric top, Euler's equation of motion, there I will write this expression for omega x dash directly. So you must remember it, okay. And similarly, the y dashed component of the resultant angular velocity omega, which is denoted by omega y dashed, that will be equal to omega phi y dashed plus omega theta y dashed plus omega psi y dashed. And when you will put all these values from this equation 5, then you will get omega y dashed is equal to this much, okay. And similarly, omega z dashed is sum of omega phi z dashed plus omega theta z dashed plus omega psi z dashed. And all these z components are defined in this equation 6. And let us substitute these values and you will get omega z dashed is equal to this much. Actually, this last expression is most important. In physical problem, omega z dashed is is actually needed several times, okay. So in this way we have obtained the x, y and z components of the resultant angular velocity omega, which is given as omega x dashed I dashed plus omega y dashed j dashed plus omega z dashed k dashed, okay. We have obtained. And this, as I have told you in the beginning, that these results are most important and most most used in our physical problems in our forthcoming lectures. Although I have now to find the component of angular velocity along the space set of x's. In fact, the component of angular velocity along the space set of x's are not used as much as we use the components of angular velocity along the body set of x's. But I have discussed these things here too. Because when an independent question will be asked, it is possible that you have to write the answer of a question in which you have to find the component of angular velocity along the space set of x's. So in this case, we have to transform the x prime, y prime, z prime system to x, y, z. So definitely the process will be just reverse. So just analogous to the way which we have discussed the first part of the problem, we can do these things, okay. But in this case, since the process will be just reverse, because in first part we have seen we have changed the xyz system to x prime, y prime, z prime. Here the problem is just reverse. So in an analogous way, we can obtain the components of omega along the space set of x's, okay. In going from the body set of x's to a space set of x's, all the three rotational operations are to be performed in reverse order. That is, in this case, psi back to theta back and phi back, okay. So how we can find? Actually, this part I have done in nutshell. I have left most of the algebra for you. This is just a homework for you. You can do this. Okay. You have seen that in psi dot is along the z dashed axis. Already you have seen. Okay. This is actually z dashed axis means body z axis. Okay. And if your aim is to find the component of this psi dot along the space x, y and z axis, that will be represented by the column matrix omega psi x, omega psi y and omega psi z. And how it will be found? When you will operate the inverse of total transformation matrix A inverse on this column matrix 0 0 psi dot, because this psi dot you can see this is along z dashed axis. Okay. So here our problem is like this: x, y, z can be found by A inverse operated on x prime, y prime, z prime. Okay. Since psi dot is along z dashed axis, so x prime and y prime component of psi dot will be 0. So the first two elements of this column matrix is 0 and third is already along z dashed axis, which is psi dot. So at the place of z component, this is psi dot, you can see. Now you have already seen how we can find A inverse. A inverse, you know, is equal to AT. Okay. So you will have to put here the value of AT and then multiply that value by this column matrix. It is just a simple algebra and you can do it. So but I have not written the expression for AT here. This has been left for you just as a homework. But when you will use the expression for A inverse or AT and simplify, then you will get omega psi x is equal to this much. This is psi dot sine theta sine phi. Omega psi y is equal to this much. This is minus psi dot sine theta cos phi, and omega psi z is psi dot cos theta. So in this way you can find the x, y and z component of omega psi. Okay. Now you know theta dot, which is d theta by dt, and theta is the rotation along the nodal lines. Okay. So theta dot will be along the nodal line. Okay. Along the nodal, that is along x1 x2 axis, and so its y and z component will be 0. Okay. And a rotation phi about z dashed axis in reverse order will bring x dashed, y dashed, z dashed set to x, y, z. Okay. And hence transformation matrix D inverse, which is equal to dt, is applied. Okay. And therefore omega theta yes, not phi but theta. Here there will be theta. Okay. Okay. So you can see omega theta x, omega theta y, omega, this column matrix, this will be obtained by operating D inverse on this column matrix theta dot 0 0. Okay. And again you will put the value of D inverse which I have defined earlier and do the algebra, and then you will get omega theta x equal to theta dot cos phi, omega theta y is equal to theta dot sin phi, and omega theta z is equal to 0. So in this way we have obtained the x, y and z component of omega theta along the space x, y, z axis. Okay. Now you know phi dot, which is d phi by dt, this lies along z axis, space z axis. Okay. This lies along space z axis, and our aim here is to transform the body xyz axis to the space z xyz axis, and phi dot is already along z-axis. So no transformation is required for it, and therefore you can say that the column matrix omega phi x, omega phi y, omega phi z, this will be simply equal to this column matrix. This is along z-axis, so x and y components are 0 here, and this is 0, 0, phi dot. Okay, 0, 0, phi dot. This much. And therefore, you can see the omega phi x is 0, omega phi y is 0, and omega phi z is equal to phi dot. So in this way, we have again obtained the x, y, z component of omega psi, omega theta, and omega phi. Okay. And when you will find the omega x, which is x component of vector omega along x-axis, this omega x, okay, that will be equal to x component, sum of x component of omega psi, omega theta, and omega phi. And you have already obtained this omega theta x here, omega phi x here, and omega psi x here. So let us substitute all those values, and after substituting you will get that omega x, which is x component of omega along the space x-axis, this will be equal to this much. Okay. Similarly, omega y, this will be the sum of omega psi y, omega theta y, and omega phi y. Again substitute values of these and you will get this. And similarly, omega z is omega psi z plus omega theta z, omega phi z, and this is equal to this much. So I hope you have clearly understand how we can find the x, y, and z components of angular velocity omega of a rigid body along the body set of body x, y, z axis and the space x, y, z axis. Actually, this is furnished by the use of the transformation matrix. Okay. So actually this question may be asked independently, but this lecture is very important for understanding the fourth coming lectures where we will use these facts. Okay, thank you very much.